The concept of sets, we have already employed the word set several times in as much as the concept of sets underlies every branch of modern mathematics. It is desirable to familiarize ourselves with at least with its more basic aspects. Set notation. A set is simply a collection of distinct objects. These objects may be a group of distinct numbers, persons, food items, or something else. Thus, all the students enrolled in a particular economics course can be considered a set. Just as the three integers 2, 3 and 4 can form a set. The objects in a set are called elements of the set. There are two alternative ways of writing a set, by enumeration and by description. If we let capital S represent the set of three numbers 2, 3 and 4, we can write by enumeration of the elements. S is equal to second bracket 2, 3, 4 second bracket close. But if we let I denote the set of all positive integers, enumeration becomes difficult, and we may simply describe the elements and write I is equal to x such that a positive integer bracket close, which is read as follows: I is the set of all numbers x such that x is a positive integer. Note that a pair of braces is used to enclose the set in either case. In the descriptive approach, a vertical bar or a colon is always inserted to separate the general designating symbols for the elements from the description of the elements. As another example, the set of all real numbers greater than 2 but less than 5, call it J, can be expressed symbolically as J is equal to x such that 2 is smaller than x is smaller than 5 second bracket close. Here, even with a descriptive statement is symbolically expressed. A set with a finite number of elements exemplified by the previous given set capital S is called a finite set. Set capital I and set capital J, each with an infinite number of elements, are on the other hand examples of infinite set. Finite sets are always denumerable or countable. For example, their elements can be counted one by one in the sequence 1, 2, 3. Infinite sets may, however, be either denumerable bracketed set capital I or non-denumerable set set capital J. In the latter case, there is no way to associate the elements of the set with the natural counting numbers 1, 2, 3, and thus this set is not countable. Membership in a set is indicated by the symbol, a variant of the Greek letter epsilon for element, which is read as follows: is an element of. Thus, for the set capital S and capital I defined previously, we may write 2 is an element of S, 3 is an element of capital S, 8 is an element of capital I, 9 is an element of capital I, etc. But obviously 8 is not an element of capital S or set S. If we use the symbol R to denote, if we use the symbol capital R to denote the set of all real numbers, then the statement x is some real number can be simply expressed by x is an element of capital R. Relationships between sets: when two sets are compared with each other, several possible kinds of relationships may be observed. If two sets capital S1 and S2 happen to contain identical elements, S1 is equal to second bracket 2, 7, A, small f second bracket close, and S2 is equal to second bracket 2, f A comma 7 comma F second bracket close. Then capital S1 and capital S2 are said to be equal. S1 is equal to S2. Note that the order of appearance of the elements in a set is immaterial. Whenever we find even one element to be different in any two sets, however, those two sets are not equal. Another kind of set relationship is that one set may be a subset of another set. If we have two sets, capital S is equal to second bracket 1 comma 3 comma 5 comma 7 comma 9 second bracket close, and capital T is equal to second bracket 3 comma 7 second bracket close, then capital T is a subset of capital S. Because every element of capital T is also an element of capital S. A more formal statement of this is capital T is a subset of capital S if and only if X is an element of T, implies X is an element of capital S. Using that, the set inclusion symbols is contained in or includes, we may then write T is contained S and S includes T. It is possible that two given sets happen to be subsets of each other. Then when this occurs, however, we can be sure that these two sets are equal. To state this formally, we can have S1 is contained S2 and S2 is contained S1 if and only if S1 is equal to S2. Note whereas the epsilon symbol relates an individual element to a set, then is contained in a symbol relates a subset to a set. As an application of this idea, we may state on the basis of figure 2.1 that the set of all integers is a subset of the set of all rational numbers. Similarly, the set of all rational numbers is a subset of the set of all real numbers. How many subsets can be formed from the 5 elements in the set? Capital S is equal to second bracket 1 comma 3 comma 5 comma 7 comma 9 second bracket close. First of all, each individual element of capital S can count as a distinct subset of capital S, such as second bracket 1 second bracket close and second bracket 3 second bracket close, but so can any pair, triple or quadruple of these elements such as second bracket 1 comma 3 second bracket close and second bracket 1 comma 5 second bracket close and second bracket 3 comma 7 comma 9 second bracket close. Any subset that does not contain all the elements of S is called a proper subset of capital S. But the set A capital S itself with all its 5 elements can also be considered as one of its own subsets. Every element of capital S is an element of capital S, and thus the set capital S itself fulfills the definition of a subset. This is of course a limiting case that from which we get the largest possible subset of capital S, namely capital S itself. At the other extreme, the smallest possible subset of capital S is a set that contains no element at all. Such a set is called the null set or empty set, denoted by the symbol. The reason for considering the null set as a subject of capital S is quite interesting. If the null set is not a subset of capital S, then null set must contain at least one element X such that X is an element of capital S. But since by definition the null set has no element whatsoever, we cannot say that null set null set is not contained in capital S. Hence, the null set is a subset of capital S. It is extremely important to distinguish the symbol null set or empty set clearly from the notation bracket, second bracket, 0, second bracket, close. The former is devoid of elements, but the latter does contain an element 0. The null set is unique. There is only one such set in the whole world, and it is considered a subset of any set that can be conceived. Counting all the subsets of capital S, including the two limiting cases capital S and null set, we find a total of 2 to the power 5 is equal to 32 subsets. In general, if a set has n elements, a total of 2 to the power n subsets can be formed from these elements. Given a set with n elements, second bracket a comma b comma c dash dash small n, second bracket close, we may first classify its subsets into two categories, one with the element a in it and one without. Each of these two can be further classified into two subcategories, one with the element b in it and one without. Note that by considering the second element b, we double the number of categories in the classification from 2 to 4 is equal to 2 square. By the same token, the consideration of the element c will increase the total number of categories to 8 is equal to 2 to the power 3. When all n elements are considered, the total number of categories will become the total number of subsets, and that number is 2 to the power n. As a third possible type of set relationship, two sets may have no elements in common at all. In that case, the two sets are said to be disjoint. For example, the set of all positive integers and the set of all negative integers are mutually exclusive. Thus, they are disjoint sets. A fourth type of relationship occurs when two sets have some elements in common but some elements peculiar to each. In that event, the two sets are neither equal nor disjoint. Also, neither set is a subset of the other. Operation of sets. When we add, subtract, multiply, divide and take the square root of some numbers, we are performing mathematical operations. Although sets are different from numbers, one can similarly perform certain mathematical operations on them. Three principal operations to be discussed here involve the union, intersection and the complement of sets. To take the union of two sets A and capital B means to form a new set containing those elements and only those elements belonging to capital A, or to capital B, or to capital A and capital B. The union set is symbolized by capital A union capital B. If capital A is equal to second bracket 3, 5, 7 second bracket close and capital B is equal to 2, second bracket 2, 3, 4, 8 second bracket close, then A union B is equal to second bracket 2, 3, 4, 5, 7, 8 second bracket close. This example, which is example 1, incidentally illustrates the case that in which two sets capital A and capital B are neither equal nor disjoint and in which neither is a subset of the other. Example 2, again referring to figure 2.1, we see that the union of the set of all integers and the set of all fractions is the set of all rational numbers. Similarly, the union of the rational number set and the irrational number set yields the set of all real numbers. The intersection of two sets, capital A and capital B, on the other hand, is a new set which contains those elements and only those elements belonging to both capital A and capital B. The intersection set is symbolized by A intersection B. Example 3, from the sets capital A and capital B, example we can write A intersection B is equal to second bracket 3 second bracket close. Example 4, if capital A is equal to second bracket minus 3 comma 6 comma 10 second bracket close and capital B is equal to 9 comma 2 comma 7 comma 4 second bracket close, then A intersection B is equal to an empty set. Set capital A and set capital B are disjoint, therefore their intersection is the empty set. No element is common to capital A and capital B. It is obvious that intersection is a more restrictive concept than union. In the former, only the elements common to A and B are acceptable, whereas in the later, membership in either capital A or capital B is sufficient to establish membership in the union set. The operator symbols union or intersection, which incidentally have the same kind of general status as the symbols root, plus, divide and minus, therefore have the connotations and bracket and or. This point can be better appreciated by comparing the following formal definitions of intersection and union. Intersection A intersection B is equal to X such that X is an element of A and X is an element of capital B, second bracket close. Union A union B is equal to second bracket X such that X is an element of capital A or X is an element of capital B, second bracket close. What about the complement of set? To explain this, let us first introduce the concept of the universal set. In a particular context of discussion, if the only numbers used are in the set of the first 7 positive integers, we may refer to it as the universal set capital U. Then with a given set, say capital A is equal to second bracket close 3 comma 6 comma 7 second bracket close, we can define another set A complement or A tilde as the set that contains all the numbers in the universal set capital U that are not in the set capital A. That is, A complement, the complement of A is equal to A second bracket X such that X is an element of union and X is not an element of capital A, is equal to second bracket 1 comma 2 comma 4 comma 5 second bracket close. Note that whereas the symbol union has the connotation or and the symbol intersection means and, the complement symbol complement carries the implication of not. If capital U is equal to second bracket 5 comma 6 comma 7 comma 8 comma 9 second bracket close and A is equal to second bracket 5 comma 6 second bracket close, then A, the complement of A is equal to second bracket 7 comma 8 comma 9 second bracket close. What is the complement of capital U? Since every object bracketed number under consideration is included in the universal set, the complement of U must be empty. Thus, the complement of U is equal to empty set. The 3 types of set operation can be visualized in 3 diagrams known as Venn diagrams. In diagram A, the points in the upper circle form a set capital A and the points in the lower circle form a set capital B. The union of capital A and capital B consists of the shaded area covering both circles. In diagram small b are shown the same 2 sets circles. since their intersection should comprise only the points common to both sets, only the shaded bracket shaded overlapping portion of the two circles satisfies the definition. In diagram small c, let the points in the rectangle be the universal set and let A be the set of points in the circle, then the complement set A tilde will be the bracketed shaded area outside the circle. Laws of set operations. It may be noted that the shaded area in diagram small a represents not only A union B but also B union A. Analogously, in diagram small b, the small shaded area is the visual representation not only of A intersection B but also B intersection E, B intersection A. When formalized, this result is known as the commutative law of unions and intersections. A union B is equal to B union A. A intersection B is equal to B intersection A. These relations are very similar to the algebraic laws A plus B is equal to B plus A and A multiplied by B is equal to B multiplied by A. To take the union of three sets capital A, capital B and capital C, we first take the union of any two sets and then union the resulting set with the third. A similar procedure is applicable to the intersection operation. The results of such operations are illustrated in figure 2.3. It is interesting that the order in which the sets are selected for the operation is immaterial. This fact gives rise to the associative law of unions bracket of unions and intersections bracket close. First bracket closed. First bracket closed. A union first bracket B union C capital C first bracket closed is equal to A union B first bracket closed union capital C. Capital A intersection first bracket B intersection capital C first bracket closed is equal to first bracket capital A intersection capital B first bracket closed intersection capital C. These equations are strongly reminiscent of the algebraic laws A plus first small a plus first bracket small a plus first bracket B plus C first bracket closed is equal to A first bracket A plus B first bracket closed plus C small c and A multiplied by first bracket B multiplied by C first bracket closed is equal to A multiplied by B first bracket closed multiplied by C. There is also a law of operation that applies when unions and intersections are used in combination. This is distributive law of unions and intersections. Capital A union first bracket B intersection C first bracket closed is equal to first bracket A union B first bracket closed intersection capital A union capital C first bracket closed. A into capital A intersection first bracket capital B union capital C first bracket closed is equal to first bracket capital A intersection capital B first bracket closed union first bracket capital A intersection capital C first bracket closed. These resemble the algebraic law A multiplied by first bracket B plus small c bracket close is equal to first bracket A multiplied by B first bracket closed plus first bracket small a multiplied by small c first bracket closed. Verify the distributive law given capital A is equal to second bracket 4 comma 5 second bracket close, capital B is equal to second bracket 3 comma 6 comma 7 second bracket close, and capital C is equal to second bracket 2 comma 3 second bracket close. To verify the first part of the law, we find the left and right hand expressions separately. Left A union first bracket capital B intersection capital C first bracket closed is equal to second bracket 4 comma 5 second bracket closed union second bracket 3 second bracket closed is equal to second bracket 3 comma 4 comma 5 second bracket closed. Write A union first bracket capital A union capital B first bracket closed intersection first bracket capital A union capital C first bracket close is equal to second bracket 3 comma 4 comma 5 comma 6 comma 7 second bracket close intersection second bracket 2 comma 3 comma 4 comma 5 intersection now second bracket close. So we get from here is second bracket 3 comma 4 comma 5 second bracket close, which is example 7. Since the two sides yield the same result, the law is verified. Repeating the procedure for the second part of the law, we have left A intersection first bracket B union capital C first bracket closed is equal to second bracket 4 comma 5 second bracket close intersection second bracket 2 comma 3 comma 6 comma 7 second bracket close is equal to, we get empty set. Write A intercept first bracket capital A intersection capital B first bracket close union first bracket A intersection capital capital C first bracket close is equal to empty set union empty set is equal to empty set. Thus this law is again verified. To verify a law means to check by a specific example whether the law actually works out. If the law is valid, then any specific example ought need to work out. This implies that if the law does not check out in as many as one single example, then the law is invalidated. On the other hand, the successful verification by specific examples, however many, which is in bracket, does not in itself prove the law. To prove a law, it is necessary to demonstrate that the law is valid for all possible cases. The procedure involved in such a demonstration will be illustrated later.